Hi guys, this is the first video of the year. Fantastic. So we're going to be talking about pressure. Specifically, hydrostatic pressure. So if you remember, pressure is defined as a force distributed over an area. Therefore, the unit of pressure is a Newton per square meter, as it is force over area. So when an object is submerged in a fluid, you want to think of the fluid as a bunch of little particles. So if you remember in class, if we have a vat or a jar of marbles, and I have all these marbles in here, then each marble is pushing on each other marble. And clearly the marbles at the bottom are feeling more weight than the marbles on the top, because there's more marbles above them. But even the marbles on the top are feeling force vectors from the marbles underneath. So if we, since we're not in particle physics anymore, embrace the classical assumption, because remember, this is just an approximation, that particles are just dots. They're like little marbles. Then if we choose a marble, say we choose this marble down here, then it's feeling the force vectors coming from all directions. So we call those the pressure vectors, right? So, I'm sorry. Those are the force vectors caused by the pressure. So each vector is a force caused by the pressure exuded from all directions. So pressure actually is a scalar that is associated with a force, which is a vector. Okay, so it's a subtle difference there. Pressure is the number, it's the distribution of that force vector over an area. It itself, though, is coming from all directions, so has no preferred direction. So the point is, if I pick, say I pick this one, if I pick a random marble, notice how the marbles around it are pushing on it from all directions, and notice how the force is then coming from almost random angles. And of course, if we make these balls tinier and tinier, we have almost infinite arrows. Each ball is surrounded by infinite balls. Right? So what is the formula then for hydrostatic pressure? So the hydrostatic pressure is defined by pressure being submerged in a fluid. So if I draw this as now just a tank of fluid, and I put an object in it, let's say I put a flat plate of some area A, and it is at some depth D. Then, so this is supposed to match up to here. I'm sorry for my drawings if they're not so accurate, but this is supposed to match up to here, and of course this is the top of the fluid. We'll say it's water, but it could be anything. So the fluid has some density. We'll call it density FL. That's density FL for fluid density. And this has area A. So imagine, so we're looking at it side on. So imagine this as being like a circular plate we've turned, and this has some area. So this is like some circle plate that we're just lying flat here in the water. Then of course the weight of the fluid above the plate, the gravitational force of that, is going to push down on the area. So therefore, the hydrostatic pressure, I'm going to write F sub g because it has to do with weight. Right? This is hydrostatic pressure, otherwise known as gauge pressure. is going to equal the weight of the fluid above the plate divided by the area of the plate. But what is the weight of the fluid above the plate? Well, we recall that weight is mass times gravity. Therefore, I'm just going to write weight as F sub g is going to be mass. But what is mass? Remember, mass in terms of a fluid is the density of the fluid times the volume of the fluid. So therefore weight is the density, or maybe I won't write fluid, maybe I'll write object. For a general object, then the weight of that is density object V object G. But my object in this case isn't the plate itself. My object in this case is the fluid, right? So I hope that that's not confusing. But the density of the fluid times the volume of this fluid times G will give us the weight. So it's the density in general. This is true. So this is in general. Specifically for this fluid here, we have the volume above the plate, right, times the fluid. So it's this little orange section here, right? So it's like this fluid here, right, is the weight we're looking at, right? So that's what we want. That's pushing on the plate, so it's the density of the fluid times that volume times G over the area. So we're almost done. The point is, what's the volume above the plate? Well, volume, so if you think of like a cylinder of area A and length L, you might say length D for distance, right? The volume is the area times that distance. This could be a square, this could be a star, it could be the shape of a dinosaur, it doesn't matter. If it's extended over a distance D, the volume of that three-dimensional surface, three-dimensional shape will be that area times the distance. So volume is A times D. Boop. So the A's cancel. And you get that is the density of the fluid times the depth times G. So the hydrostatic pressure is the density of the fluid times the depth times G. So let us go to an example. And I will remind us, I'm going to rewrite the equation. So feel free to pause that before or re-listen to it if you need to remember that explanation. But hydrostatic pressure is rho d. G. Is this the density of the object? No. It's the density of the fluid. So let us compare different objects, different depths. Let's say I have a turtle, I have a submarine. The turtle has volume V, submarine has volume 100 V. They are both at 10 meters. Yes, this is a submarine. This is a turtle. They're both in water. What is the pressure that the turtle feels? We'll call it P1. We'll call the pressure the submarine feels P2. Which feels more pressure? Well, the density of the fluid, H2O, is 1,000. The depth is 10, and G is 10. So we have 10 times 10 equals 100,000 newtons per square meter. Oh, by the way, I should have said this before. I said this yesterday, but a Newton per square meter is a Pascal. PA. So this is 100,000 pascals, which I will rewrite in proper prefix notation as 100 kilopascals. So you might think, oh, okay, this submarine is bigger, right? It's 100 times bigger, so it has 100, well, it's 100 times bigger volume-wise, but it definitely has a bigger area. Above it, there's therefore more water. But if we distribute that water over a bigger surface, the pressure stays the same. That's the key here. Pressure is force distribution. Remember, it has to do with force, and those force vectors are pushing in all directions, right? So we have force vectors here, force vectors here, force vectors here. Those little molecules of water are pushing, 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 right? So we have force molecules here, forces here, forces here, right? So I didn't mean to draw these bigger. But the point is the force molecules here are going to be the same as the force molecules here. There's more force vectors here, but they're distributed in the same way that they're distributed over the tool. Because there's a bigger area for them to distribute over. Or, if you trust the equation, look, did the density of the fluid change? Absolutely not. Did the depth change? Absolutely not. Did gravity change? Absolutely not. So both are 100,000 or 100 kilopascals. Pressure only depends on the density of the fluid and, most importantly, the depth. So clearly, if the depth, so say this turtle were to come down here, and the turtle were to come to a depth of 100 meters, or we'll say 50. That's about 5. Let's do it to scale. 1, 2, 3, 4, 5. 50 meters. What would happen to the pressure? Well, clearly, it's the same turtle, 5 times the depth, therefore 5 times the pressure. So notice how the pressure only depends on how much fluid is above in terms of depth, not in terms of area. In fact, this is really important. This is the density of the fluid, this is the depth, and this is gravity. Say this object, this turtle has a certain density object, and say this has some certain density object. Does the density of the object affect what's pushing on it? Absolutely not. Does the size of the object affect what's pushing on it? Absolutely not. Does the shape of the object affect what's pushing on it? Absolutely not. There is no property of the object. So actually I'm going to word that differently. I'm going to say it's independent of any property of the object. Isn't that cool? I think that's a really important connection to make. Doesn't matter what it is, turtle, submarine, even if it's like an air bubble that's really light and it's floating to the top, and you're like, wait, but that has a density of air, right? This has a density of metal. Isn't that the same thing? Well, clearly this is filled with air too, by the way, obviously. Even if you had like a steel ship here sinking, or something floating, at that instantaneous point, wherever the depth is, it's going to have the same pressure. As we're going to discover, I'm giving a secret hint away, but this is an important thing, so I'm just going to say it. I don't want to keep things secret. These force vectors are pointing up. They're not pointing down. Right? Because all those marbles are pushing on each other. They're squeezing. Pressure squeezes from all directions. Therefore, the bottom experiences a force up, the top experiences a force down. Which is at a greater depth? This is. So that'll lead us into buoyancy. Okay? So just remember that pressure does not have a specific orientation when something's submerged. And it only depends on that. And the pressure, and the density of the fluid and gravity. But if you're in water and you put a bunch of different things in water, it doesn't matter. All that matters is depth. Cool, guys. See you in class.